There are moments in the history of science when everything appears calm on the surface, yet underneath, reality is quietly rearranging itself. No alarms, no flashing lights, just a subtle shift in probability, invisible to the naked eye, but profound enough to change the trajectory of entire civilizations. Tonight's story begins in one of those moments, a moment so fleeting that most people pass through it without noticing. A moment that exists right at the edge of what physics can describe and what consciousness can perceive. A universe where the future is not fixed, where countless possible outcomes coexist, stacked on top of one another like transparent sheets of glass. Every decision, every observation, every measurement presses down on that stack, causing one possibility to harden into reality while the others fade away. This is not mysticism. This is not fantasy. This is the uncomfortable implication of modern physics. And according to some of the most serious minds of the last century, there may be brief instants when those possibilities reshuffle, when the universe itself hesitates. If you were alive during one of those instants, you would not hear a sound. You would not see the sky tear open. You might be sitting in traffic, scrolling on your phone, or staring at the ceiling at 3 in the morning. Yet something fundamental would be happening beneath the surface of existence. The equations would still hold, the laws would still apply, but the probabilities would be in motion. Physicists have a name for the mathematics behind this instability. Philosophers have a name for the experience of sensing it. Historians, looking backward, often only recognize it after the fact, when the world before and the world after no longer resemble each other. We call these transitions revolutions, paradigm shifts, or breakthroughs. But at the deepest level, they resemble something closer to a quantum jump. A quantum jump is not a leap through space. It is a discontinuity. An abrupt change between allowed states, with no smooth path in between. In the quantum world, particles do not gradually slide from one energy level to another. They vanish from one state and reappear in another, as if reality briefly forgot how to be continuous. For decades, physicists believed this strange behavior was confined to the microscopic realm, atoms, electrons, photons. But what if the same logic applies, in some form, to larger systems, to brains, to societies, to moments in history when the old explanations stop working and new ones suddenly take their place? What if there are thresholds where observation itself becomes decisive, where being present at the right instant changes which version of reality survives? Tonight, we are not promising revelation. We are not offering certainty. What we are offering is a careful, serious journey through the science, the history, and the limits of what we know. A journey to the narrow boundary where physics becomes philosophy, where measurement becomes meaning, and where the universe briefly opens a door before closing it again. You will only see this once, not because the video disappears, but because the moment it describes is already passing, and by the time you understand it, the jump may already be underway. Kel to asita, and if you value deep, calm explorations of science and the universe, subscribe to the channel, like this video, and leave a comment. In your comment, answer this question: which part of the country are you watching from? Shieptr1Te star NGSIDA and Madarn PHYCS. To understand what a quantum jump truly is, we have to begin with a confession that physics rarely makes out loud. At its core, modern physics does not describe reality as it is. It describes reality as it is observed. This distinction, subtle at first, becomes unsettling the longer you sit with it. At the end of the 19th century, physicists believed they were approaching the final chapter of their discipline. The laws of motion were known. Electromagnetism had been unified. The universe appeared to be a vast clockwork machine, ticking forward with perfect predictability. Given enough information, the future could, in principle, be calculated exactly. This worldview left little room for surprise, and even less for mystery. Then, almost without warning, the clockwork began to fail. The first cracks appeared in experiments that should have been simple. When scientists tried to explain how hot objects emit light, classical physics produced results that were not just wrong, but absurd. According to the equations, a heated object should emit infinite energy at high frequencies. This so-called ultraviolet catastrophe was not a minor error. It was a sign that something foundational was broken. In 1900, Max Planck introduced what he believed was a mathematical trick. He proposed that energy is not exchanged continuously, but in discrete packets he called quanta. Planck himself did not initially believe this reflected reality. It was a convenient assumption, a way to make the equations behave. But nature, it turned out, took the idea seriously. Within a few years, Albert Einstein extended the concept to light itself, suggesting that electromagnetic radiation comes in particles later called photons. Suddenly, light was no longer purely a wave. It had a dual nature, behaving sometimes like a spread-out oscillation and sometimes like a localized particle. This was not just strange. It was logically incompatible with classical intuition. As experiments piled up, physicists were forced to accept a disturbing conclusion. At the most fundamental level, the universe does not commit to a single definite story until it is measured. Before observation, physical systems exist in a superposition of possibilities. Not one outcome, but many. The act of measurement does not merely reveal a property. It selects one. This is where the quantum jump enters the story. In atomic physics, electrons occupy specific energy levels. These levels are not arbitrary. They are fixed by the structure of the atom and the rules of quantum mechanics. An electron cannot exist between them. When it absorbs or emits energy, it does not move smoothly from one level to another. It jumps. The transition is instantaneous, with no defined process connecting the before and the after. For years, this behavior was treated as a curiosity of the microscopic world. Atoms are small, quantum effects are weird, end of story. But as the theory matured, it became clear that the mathematics of quantum mechanics does not contain a size limit. In principle, superposition and discontinuous transitions apply to all physical systems. In practice, interactions with the environment cause larger systems to lose their quantum coherence almost instantly. This process, known as decoherence, is why tables do not exist in multiple places at once. Yet decoherence does not eliminate the underlying structure of quantum theory. It hides it. The jump is still there, buried under layers of interaction and noise. And this raises a question that physicists and philosophers have been circling for decades. If the fundamental fabric of reality is probabilistic and discontinuous, what does that say about change at larger scales? One of the most controversial ideas to emerge from this tension is the role of the observer. In quantum experiments, the outcome depends not only on the system being measured, but on how it is measured. Different experimental setups produce different realities. This is not because the experimenter influences the result through intention or belief, but because measurement itself is a physical interaction that constrains what can happen. The famous double-slit experiment demonstrates this with uncomfortable clarity. When particles such as electrons are fired through two slits without being observed, they create an interference pattern characteristic of waves. When detectors are placed to observe which slit each electron passes through, the interference disappears, and the electrons behave like particles, the mere availability of which path information changes the outcome. This does not mean consciousness creates reality. That interpretation goes far beyond what the data supports. But it does mean that reality at the quantum level is not independent of observation. The universe is not a static object waiting to be revealed. It is an ongoing process, shaped by interactions. Some physicists, such as Niels Bohr, embraced this ambiguity, arguing that physics is not about describing an objective reality, but about predicting the outcomes of experiments. Others, like Einstein, were deeply uncomfortable with the idea, insisting that something real must exist beneath the probabilities. His famous objection, that God does not play dice with the universe, was not a theological statement, but a demand for deeper explanation. Over time, multiple interpretations of quantum mechanics emerged, each attempting to make sense of the same mathematics. The Copenhagen interpretation accepts the primacy of measurement and the collapse of the wave function. The many worlds interpretation denies collapse altogether, suggesting that all possible outcomes occur, each in its own branching universe. Objective collapse theories propose that wave functions spontaneously collapse, independent of observation at certain thresholds. What unites these interpretations is their acknowledgement of discontinuity. Whether through collapse, branching, or spontaneous jumps, the transition from possibility to actuality is not smooth. It is abrupt. Something changes, and the theory does not describe the mechanism in classical terms. This is where the metaphor of a quantum jump begins to resonate beyond physics. In human experience, there are moments when change feels discontinuous, when the gradual accumulation of pressure, information, or instability suddenly resolves into a new state. Revolutions do not occur because of a single event. They occur because a system reaches a tipping point. In science itself, paradigm shifts follow this pattern. For years, anomalies accumulate at the edges of accepted theory. They are explained away, ignored, or treated as errors. Then often suddenly a new framework emerges that reorganizes the entire field. Afterward, the old questions no longer make sense in the same way. The jump, in retrospect, feels inevitable. But living through it, it feels uncertain and unstable. The idea that we might be approaching such a threshold in our understanding of reality is not speculation without basis. Advances in quantum information theory, experiments with macroscopic superpositions, and the ongoing struggle to reconcile quantum mechanics with gravity all point toward unresolved foundations. We are using theories that work extraordinarily well, without fully understanding what they mean. At the same time, our technological ability to manipulate quantum systems is increasing rapidly. Quantum computers exploit superposition and entanglement not as philosophical curiosities, but as engineering resources. In doing so, they force us to confront questions about measurement, decoherence, and control at scales that were once purely theoretical. The more we build, the less abstract these ideas become. The quantum world is no longer confined to laboratories and thought experiments. It is entering infrastructure, communication, and computation. With that transition comes a subtle shift in perspective. The line between observer and participant begins to blur. None of this implies that individuals can will reality into existence. That claim belongs to metaphysics, not physics. But it does suggest that reality is less rigid than classical intuition would have us believe. The future is constrained, but not fixed. The present is stable, but not immutable. And change, when it comes, may not announce itself gradually. A quantum jump, in the strict physical sense, is defined by allowed states and forbidden gaps. The system cannot exist in between. If the analogy holds even loosely at higher levels, it suggests that there are periods when incremental adjustment is impossible, when a system must either remain as it is or transition entirely to a new configuration. Understanding this does not give us control, but it gives us awareness. It reframes moments of instability not as failures, but as boundaries, and it reminds us that what feels like stillness may in fact be the pause before a transition. If quantum jumps were confined entirely to atoms and particles, their relevance to human experience would remain mostly philosophical, fascinating but distant. Yet the more closely scientists study the brain, the more they encounter patterns of change that resemble discontinuities rather than smooth progressions. Not quantum jumps in the strict physical sense, but transitions that share a similar structure: long periods of stability followed by abrupt reorganization. For most of the 20th century, neuroscience described the brain as a classical machine. Neurons fired or remained silent. Signals traveled along well-defined pathways. Learning occurred gradually through incremental changes in synaptic strength. This picture was not wrong, but it was incomplete. As measurement techniques improved, researchers began to notice something strange. Large-scale brain states did not always change smoothly. They snapped. Electroencephalography revealed sudden shifts in global brain activity during perception, decision-making, and consciousness itself. Functional MRI studies showed that networks of brain regions reorganize abruptly when a person becomes aware of a stimulus or reaches a decision. The transition from not seeing to seeing, from uncertainty to commitment, is not a slow ramp. It is a rapid reconfiguration. This posed a problem for classical intuition. If the brain is merely a collection of neurons obeying local rules, why do global patterns emerge so suddenly? Why does awareness feel like a switch rather than a dimmer? Why does insight arrive as an aha moment instead of a gradual realization? To answer these questions, some neuroscientists turn to ideas borrowed from physics. One of the most influential is the concept of criticality. In physical systems, critical points occur at the boundary between order and disorder. Near these points, small perturbations can produce large effects. A magnet near its critical temperature can suddenly lose its magnetization. A fluid near boiling can erupt into turbulence. Evidence increasingly suggests that the brain operates near such a critical point. Neural activity hovers between stability and chaos, allowing it to be both flexible and reliable. In this regime, information processing is optimized and transitions between states can occur rapidly. A small input at the right moment can reorganize the entire system. This does not mean the brain is quantum mechanical in the way atoms are. Most neuroscientists agree that quantum coherence does not persist in warm, wet neural tissue for long enough to influence cognition directly. Claims that consciousness arises from quantum effects inside neurons remain speculative and controversial. But the analogy to quantum jumps is structural rather than literal. What matters is the pattern of change. The brain accumulates information, tension, and probability over time. Then, when a threshold is reached, it transitions abruptly into a new state. Before the transition, multiple outcomes are possible. After it, one outcome dominates. Consider decision-making. Experiments show that neural activity associated with different choices builds up in parallel. Competing networks represent alternative actions. For a time, none of them wins. Then suddenly, one pattern suppresses the others and the decision is made. Subjectively, this feels instantaneous. Objectively, it reflects a nonlinear transition in network dynamics. The same pattern appears in perception. When viewing an ambiguous image, such as a drawing that can be seen as either a vase or two faces, the brain does not blend the interpretations. It flips between them. At any given moment, one interpretation dominates completely. The transition between them is sudden, unpredictable, and uncontrollable. These phenomena suggest that consciousness itself may be organized around discrete states rather than a continuous flow. From this perspective, awareness is not a smooth stream but a sequence of stable configurations punctuated by rapid transitions. This idea has deep implications. If mental states change discontinuously, then moments of transformation are not evenly distributed. They cluster around thresholds. Most of the time, the system resists change. Then, briefly, it becomes exquisitely sensitive. Psychology has long recognized this pattern, even without the language of physics. Sudden insights, emotional breakthroughs, and shifts in identity often occur after prolonged periods of stagnation. Therapy does not progress linearly. Learning does not advance at a constant rate. History, too, reflects this rhythm. What neuroscience adds is a mechanistic framework. It suggests that these transitions are not mysterious in a supernatural sense. They are emergent properties of complex systems operating near criticality. The brain is not special because it breaks the laws of physics. It is special because it exploits them. Yet this raises a deeper question. If the brain is a physical system subject to the same probabilistic rules as everything else, what role does experience play? Where does meaning enter the picture? Here, the observer effect returns, not as a claim that consciousness collapses wave functions, but as a reminder that measurement and interaction are inseparable. The brain does not passively receive information about the world. It actively samples, predicts, and interprets. Every act of perception is also an act of selection. Modern theories of cognition increasingly describe the brain as a prediction machine. It continuously generates models of the world and updates them based on sensory input. When predictions fail, error signals propagate through the system, forcing revision. Most updates are small. Occasionally, they are not. When accumulated prediction errors exceed a certain threshold, the brain abandons its current model and adopts a new one. This is not a gentle revision. It is a restructuring. What was previously meaningful becomes irrelevant. What was invisible becomes obvious. The world subjectively changes. From the inside, this can feel like a sudden awakening or a loss of certainty. From the outside, it is a system optimizing itself under constraint. Again, the structure mirrors the quantum jump. Multiple interpretations coexist. One becomes untenable. Another takes its place. Importantly, these transitions cannot be forced directly. You cannot will yourself into insight any more than you can force an electron to occupy a forbidden energy level. You can only change the conditions. You can add information, increase pressure, or alter context. The jump occurs when it occurs. This perspective casts new light on the idea of being, right before, a transition. In physical systems, the moments preceding a critical transition are marked by subtle signals. Increased fluctuations, slower recovery from perturbations, heightened sensitivity. Scientists call this critical slowing down. In the brain, similar signs appear. Heightened emotional volatility, increased rumination, a sense of instability or uncertainty. These are often interpreted as symptoms to be eliminated, but from a systems perspective they may indicate proximity to change. This does not romanticize suffering or instability. Many systems fail instead of transitioning. Not every threshold leads to a higher-order organization. Collapse is also possible. The point is not inevitability, but potential. Understanding this helps clarify the limits of popular narratives about manifestation and mental control. The brain does not create reality in a literal sense. It creates internal models that guide action. Those actions, in turn, influence external outcomes within the constraints of physical law. There is no mechanism by which belief alone alters the behavior of particles at a distance. But there is a well-established mechanism by which belief alters behavior, attention, and decision-making, which then cascade into measurable effects. The jump, when it occurs, is not magical. It is emergent. The danger lies in confusing metaphor with mechanism. Quantum language is seductive. Words like superposition, collapse, and entanglement carry a sense of depth and mystery. When applied carelessly, they blur the line between rigorous science and wishful thinking. A serious account must maintain that boundary. The brain exhibits discontinuous transitions because it is a complex, nonlinear system, not because it directly harnesses quantum phenomena. The similarity in structure does not imply identity in cause. Yet even within this sober framework, the implications are striking. If the mind changes through thresholds rather than smooth accumulation, then timing matters, context matters, observation matters. Being present at the moment of transition, whether in learning, creativity, or understanding, is not about witnessing fireworks. It is about recognizing that what comes after cannot be reached by adding more of what came before. This recognition reframes uncertainty. It suggests that periods of not knowing, of instability, of apparent stagnation are not empty, they are preparatory. The system is exploring its state space, accumulating probability, approaching a boundary. From the outside, nothing appears to be happening. From the inside, everything is in motion. As we move outward, from brains to societies, from neurons to networks of people, the same patterns emerge again. Systems resist change until they do not. Information accumulates. Tensions rise. Then, abruptly, a new order appears. In physics, once the jump has occurred, the system settles into a new state. The equations resume their calm precision. The instability is gone. What remains is a new baseline, one that feels inevitable in hindsight, even though it was undecidable before it happened. This is one of the most unsettling truths science has uncovered. The universe is lawful but not scripted. The past constrains the future, but it does not dictate it in detail. At critical moments, multiple outcomes are genuinely possible, and only after one is realized does it begin to look like it was always meant to be that way. When physicists describe a quantum jump, they are not describing drama, they are describing resolution. The system has stopped wavering. One possibility has been selected. The others are no longer accessible. From that moment on, the system evolves smoothly again, as if nothing strange ever occurred. This is why quantum jumps are so easy to miss. They leave no scar. They do not announce themselves. They simply redraw the boundary conditions of what comes next. At larger scales, the same pattern holds. After a scientific revolution, textbooks are rewritten. New students learn the new framework as if it were obvious. The older debates fade into footnotes. The uncertainty that preceded the shift becomes difficult to reconstruct, even for those who lived through it. After a societal transformation, norms realign. Behaviors that once seemed unthinkable become ordinary. What was once controversial becomes assumed. The jump, once completed, disappears into the background of daily life. This is why the moment before the jump matters more than the moment after. Before the transition, the system is open. Multiple futures coexist. After it, the path narrows. From the perspective of physics, there is nothing mystical about this. It is the natural behavior of systems governed by probabilistic laws and nonlinear dynamics. But from the perspective of lived experience, it feels profound. It is the difference between standing at a crossroads and walking down a road. Importantly, science does not tell us which outcome will occur. It tells us the space of possibilities and the constraints that shape them. It tells us when a system is stable and when it is near a threshold. It does not tell us what it is like to be inside that threshold. That interior experience belongs to consciousness, not as a force that bends reality, but as the only place where uncertainty is felt. Particles do not wonder which state they will occupy. Systems do not feel tension as they approach criticality. Humans do. This does not grant us special power over the universe. It grants us perspective. To be conscious at a moment of transition is to inhabit a narrow window where the future has not yet hardened. This does not mean the future is arbitrary. It means it is conditional. Small differences in timing, context, and interaction can matter more than they do during periods of stability. This is why periods of uncertainty often feel amplified. Emotions run hotter, information feels heavier, decisions feel more consequential. The system, whether a brain, a society, or a scientific framework, is more sensitive than usual. Once the jump occurs, that sensitivity fades, stability returns, the urgency dissolves. People often look back and wonder why things felt so intense. They assume they were mistaken. They assume the tension was imagined. Physics suggests otherwise. Near a critical transition, fluctuations increase. Recovery slows, signals are amplified. The system is not malfunctioning, it is preparing to change. There is a temptation to romanticize this idea, to see every moment of discomfort as a sign of imminent transformation. Science does not support that conclusion. Many systems hover near instability, and then settle back into their original state. Some collapse entirely. Some never find a new equilibrium. A quantum jump is not guaranteed. It is permitted. What science offers is not prophecy, but literacy. It gives us language for understanding why change often feels sudden, why history moves in fits and starts, and why the present can feel strangely suspended at times, as if waiting for something to resolve. The title of this story speaks to that suspension. You'll only see this once does not mean the universe sends secret messages to individuals. It means that moments of openness are temporary. They close whether or not we are paying attention. Right before a quantum jump, the world looks ordinary. The equations still work. The routines still hold. But beneath the surface, the distribution of possibilities is shifting. After the jump, the question is no longer what might happen. It is what happens next. And that is the quiet, unsettling beauty of the universe as science reveals it. Not a rigid machine, not a wish-fulfilling dream, but a structured, probabilistic reality where change is real, thresholds exist, and the future is shaped at moments so subtle they are almost invisible. If there is any lesson to take from this, it is not about control. It is about awareness, about recognizing that stability is not permanence and uncertainty is not emptiness. They are phases of the same process. The jump does not announce itself. It never has. By the time you are certain it occurred, it is already part of the past. And whatever state the universe settles into next will feel, once again, like the only one that ever made sense.